Good evening, guys. I have two of you. We'll wait for a few more minutes. Okay, we'll start. So, as you have said, we'll start with coordination compounds, right? Okay, so you have asked me for certain topics like IUPAC naming, isomerism, and I wanted to teach you crystal field theory, right? So, these three are the areas which we'll be concentrating our time on, right? Okay. We already know what are coordination compounds, right? So we, from the name itself, it tells you that the type of bonds are going to exist in this kind of molecules is going to be a coordinate covalent bond, right? So we know this is a coordinate bond rather than one electron coming from each species. There is going to be two electrons coming from one species, and that is going to be donated to the other species, right? Okay, so that is one thing, right? And okay, I hope you know the terminologies, right? So whatever is going to be inside this bracket is what is called as coordination sphere, right? And I have inside this coordination sphere, I have a central metal atom, right? And also I have something called as ligands, right? N number of ligands, whatever it is. And outside this, I can have some kind of cation or anion, right? That is what is called as your counter ion, right? So these are some, and you know how to calculate the coordination numbers, you know how to calculate the oxidation numbers of all these species. Basically, you have to keep in mind the oxidation number for the metals. That's what you need to calculate, right? And if at all you want to be very good at this topic, you need to know what are the group numbers of all these D block elements, right? So now if you start, say it will be scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So this order you need to remember. Okay, so this order you need to confirm, like for sure you need to remember, right? And along with the atomic numbers, if you can start, so obviously scandium starts with 21 and zinc ends with 30. Okay, so now if you remember this, you can easily tell what will be the configuration. Now for all these D block elements, I will have D 1 to 10, or I would say n minus 1 D 1 to 10, 4s or n s2. Okay, so n will be the valential, n minus 1, so it will be basically 4s and 3d, right? And if I go for 4d series, it will be 5s and 4d, and same way for 5d series, it will be 5d and 4s, sorry, 5d and 6s. Okay, so you have to remember the configuration. So now you can easily tell what will be the configuration here. So now it is going to be actually n, or I would say for scandium it is going to be 3d1 4s2. Same way, this is going to be titanium is going to be 3d2 4s1 of it 4s2. So like that, like that, like that. Chromium alone will have a small thing. So you'll have 3d5 4s1, right, because of half fill stability, right? And for copper, oh sorry, this will be 3d1 3d2 3d3 3d4, okay, correct. So 3d5 4s1 because of half fill stability, right? And for copper again, you will have something like this 3d10 4s1. Again, here in this corner because of fully fill stability of the deconfiguration, and this will have 3d10 4s2 at last for zinc, right? So these things you have to remember, okay, for calculating so many stuffs, right? Okay, so that is one thing, right? So, and if you can remember what are all the groups present, I mean, what are the elements present along with these groups? Say for example, along with nickel I'll have palladium and platinum, along with zinc I'll have cadmium and mercury, right? Say for like this, say I have iron will have ruthenium and one more thing which I forgot. So like this, if you have to remember, like if you can remember all the three elements, 4D, 3D, 4D, 5D, for all the groups, right? That might also be helpful. Like 99% of times they will be giving you only 3D series, right? But you can have questions or like just that they're going to have same configuration. Like if at all I'm going to take say nickel, nickel is going to have 1 2 3 4 5 6 7 8, so it's going to have 3d8 4s2, right? Say palladium will have 4d8 5s2, like that it is going to be, right? So if you can remember what are the other elements present in that particular group, that also will be very helpful, okay, right? So these things you have to know. Next, okay, we'll directly go for IUPAC naming, right? So for IUPAC naming, what you have to understand is, obviously, I'm now first. This is going to be normal. Whatever the rules you follow for naming of normal compounds, right? The first things first. You'll always have to name the cation first, and then only the anion. Anion next, right? You have to name the cation first, and then only you have to go for anion. That is one thing. Again, it can be a cationic complex. If it's a cationic complex, you'll name the this things in the sphere, coordination sphere. For example, if this is the coordination complex, this is having a positive charge, and there is some X minus, right? You will name this first and then go for this, right? Or if it is other way around, for example, if I have like say FeCN 6 times 4 minus K4, I mean 4K plus, whatever it is, right? Now in that case, you are going to have this name first and then the coordination sphere. So whatever it is, right? So the cation has to be named first, and then you have to name the anion. That is first thing. Second thing is that, okay, fine, you have decided what is the cation, what is the anion, right? Next thing what you have to know is, if you okay, obviously now if you're going to concentrate on the coordination sphere, right? When I go for the coordination sphere, the metals is name first come first, right? Oh, sorry. First the ligand, basically the ligand, then you go for metal along with the oxidation state. Whatever the oxidation state, that also has to be named along with it. Okay, and the third thing is that you have to remember the names for each and every ligand possible, right? Say if it is going to be Cl, it is going to be chlorido, right? Say for H2O, it is going to be aqua, right? Say now if I have EDTA, I write it as EDTA only, right? I mean, or you can write it as ethylene diamine tetraacetate fully. So like that, you have to remember the ligands' names. Okay, so ligand's name, obviously the oxidation number, you should know how to calculate, right? And obviously you should know what is the cation and what is the anion. And it is not only this, you have to remember the names. Also, what you have to follow is, when you're going to name the ligand, that has to be done in alphabetical order. Right, that has to be named in the alphabetical order. Okay, so maybe now we'll take some examples. Now you know the rules, right? So let us take some examples and we'll try to name them. Okay, right? Okay, let me get some examples. Okay, say I take Ag NH3 twice Cl. Okay, so I take this compound. Okay, right. So now you can easily understand that this is going to be the anion, this is going to be the cationic complex here. So obviously I have to name this first, right? So when I'm going to name this first, you have to understand that I have to name the ligand first, right? Inside the coordination sphere. Whether you do it first or second doesn't matter. But once you go to the coordination sphere, you have to name the ligands first, right? So ligands first, I have amine as the ligand, right? And you have to specify how many such type of ligand is also present. That's like how you do in your organic IUPAC naming, right? So here it is going to be diamine. Amine is the ligand name, di because it has two, right? Diamine silver, right? Now I told you have to write it along with the oxidation states, right? So you can easily calculate the oxidation state. Say for iron, for Ag, if it is X, this is a neutral ligand. Again, you want to know what type of ligand is also there, right? Ammonia, H2O, EDTA, no, ammonia, H2O, any amines, right? So all these things will be neutral ligands. They will not impart any charge to the metal center, right? Their only role is to donate the electrons in the form of a coordinate bond, right? So if it's a neutral ligand, you put the charge as 0. If at all you have any other charge, say for example, if it is O2 or oxygen, it is going to be O2 minus. So at that time it will be -2. If it was like any other thing like chlorine, bromine, iodine, fluorine, all these things, that time it will be -1, right? So Cn minus will have -1. Carbon monoxide again will be a neutral ligand, right? So those things has to be taken care. Okay, so this is X and this is amine, and so also it is 0. Now if you can just remove this one Cl minus, you'll get a +1 here, correct? So or yeah, +1 here. So X is equal, X plus 0 is equal to +1. The overall charge on this is +1. So I can easily write silver is in +1 oxidation state, and that has to be done with the help of Roman numbers. Okay, whenever you write the oxidation state will be in terms of Roman numbers, not normal numbers. Okay, Roman numbers. So diamine silver. So that's it. This is about this part, and I have a chlorine. And obviously, whenever you talk about anion, you have to end with IDE. Okay, you have to end with IDE. So it is chlorine is there, so it has to end with chloride. Okay, right, fine. So let me take some other thing. Okay, say if I have to, now let me take an anionic complex. Say I have K4 FeCN 6 times. I have this molecule. Now in this case, you see that I'm going to have the anionic complex, right? The complex, the coordination sphere is anionic. It is going to have a negative charge. So obviously I have to write the cation's name first. In that case, it is potassium. Potassium, right? Okay. Now again, when you go to the coordination sphere, you have to name the ligand first, right? So it will be hexa cyano. Cyano is the name of the ligand. Hexa because I have 6, right? Now, please understand, people. Last time you just wrote diamine silver because it is going to be in the form of a cation, right? Now, whenever you see the coordination sphere is anion, right? Please remember you have to write it as metallate. You have to end it with metallate. ATE should you that's what it should end with, right? So in this case, you see it is iron, right? So I'm going to call it as ferrate, and you can easily calculate the oxidation state. Oxidation state, if you calculate, it will be +2. So ferrate 2, potassium hexacyanoferrate is what is the ferrate 2 is what is the name of this complex. Okay, so hope you understand. Whenever you have the cationic complex, that anion, the counter anion, should end with IDE, right? And whenever you have a anionic complex, right, at that time it has to end with metallate, ferrate, zincate, aluminate, something like that. Okay,
Sir,
right.
always name from left to right, no, sir.
Always.
Name from left to right, something like that.
Yeah,
Sir.
always name them left to right. That is also cool. That is also a good thing. Anyways, why now when we write a chemical formula also, we follow this. We always write the cation first and then write the anion. NaCl, I don't write the ClNa. I write the cation first, Na plus, then the Cl minus. That's how I write it also. That also, if you follow it, is fine for me.
Sir, so it's
Okay.
like first write the cation, and then in the complex you write the cation later. If it's like if the ligand is in, if the complex sphere is in the right hand side.
If the complex pair is in right hand side, for sure it is going to be an anionic complex. You can make sure that that's how it is going to be.
Yeah, sir.
Okay.
For that, inside the complex sphere, if there's a cation, you write that in the end.
Yeah,
For
obviously,
example,
right. No. Don't confuse yourself. When it is going to be at the right, it is always going to be the anionic complex. That has to come after the cation. Okay. Then if you go to this coordination sphere, whether it is cation or anion, you have to write the ligand first, then only the metal.
oh, okay, sir. Okay, sir.
Understood?
Yes.
Right? Okay. Right. Say some other example. Do this is my duster. Yeah. Okay. Okay. Say if I have CO, En twice, Cl2, is it plus? Yeah, plus. Okay. Now, guys, you hope you know what do you mean by denticity of a ligand, right? So when I say denticity, it is the number of donor sites that particular ligand can have, right? So you have monodentate ligands. Monodentate ligands will have only one site. For example, say Cn minus, CO, X minus, any fluoride or halide, OH minus, H2O. All these are actually going to be your monodentate ligands, right? Now you have something called as didentate, tridentate, polydentate ligands. Say now if you look at this ethylene diamine, En is basically going to be ethylene diamine. Ethylene diamine's abbreviation is what is En, right? So if you look at ethylene diamine, this is how it is going to look. Okay, so now what you see is that there are going to be two coordination sites. Okay, there are going to be two sites from which the ligand can have a bond with the metal. Okay, so in this case, you see there are two centers, so it is going to be called as a didentate ligand, right? So you know EDTA will be a tetradentate ligand, right? So like this, the denticity of this thing also matters for naming. Okay, now if you have a monodentate ligand, you go for say bi, tri, tetra, hexa, all these numbers you mentioned, right? But if you go for a bidentate or any other polydentate ligand, and if you have more than one that type of ligand, you cannot use bi or tri. What you have to use is bis, tris, tetris, right? So like this only you should use. Okay, now you see this ethylene diamine is a bidentate ligand, and I have two molecules of that. So I should not say di, I should say bis. Okay, right? But if at all you had 3 of them, you should not tell it as tri, you should tell it as tris. Okay, so if I have to name this compound now, right, if I have to name this compound, right, so now again this is a cationic complex, there is no anion, so leave it, right? Fine. So again you have to go for your alphabetical order, right? So it is ethylene diamine, this is your chlorine, so C will come first, so I go for first dichlorido. That's done, right? Next is the en is a didentate ligand, so in this 2 of them are there, so I should use bis ethylene diamine. Right, ethylene diamine. Now this is cobalt. Now oxidation state of cobalt would be 3. You can easily calculate. Again, this will be a neutral ligand. X minus 2 is equal to plus 1, so X will be plus 3. Right, so this will be in plus 3 oxidation state. So the name of the compound will be dichlorido bis ethylene diamine cobalt 3. And if at all I had any anion, you'll include that, say cobalt 3 chloride, cobalt 3 sulfate, something like that. Okay, right. So maybe one more example.
Sir, I have a doubt.
Yeah.
Sir, whenever there's a negative ligand, should we suffix it with IDO or just O?
IUPAC now said that you have, since we have IUPAC naming in organic compounds also, right? So there we don't go for this IDO and stuff, right? But here we generally go for IDO. But again, people use both, only IDE or IDO, both they'll use. But we'll follow a universal convention. We'll go for IDO only. But the other thing is not wrong. You can use that also. Okay. Right,
So,
but
sir,
in your exams, go for IDO only. Yes.
Sir, so then in the previous example, we had cyano, right?
Oh, okay. So we wrote a cyano, it should be cyanido. Yeah, that is also okay.
Yes.
Right. So, but that's what, like that much they will not check. But yeah, it is always better to go with ending with O. That's better. It should be cyanido, oxalato. Yeah, that will also, that only will be correct. Okay. Right. So yeah, this is what you're talking about. Yeah, it's be hexacyanido. That'll be better. Right. Okay. Next question. Okay.
Sir, for amine, no, sir.
Mm.
When do you use 2 M's and when do you use 1 M, sir?
Again, both are correct. Okay. We don't have to worry about it. But generally, in your NCERT textbooks, they would have given as double M. Generally, that's what they use. Go for that only.
Sir,
But
my
again,
teacher
there's no,
cut marks for me, sir, for not using double M. I mean,
oh,
for using double M, sorry.
for using double M, she cut marks.
Yes, sir. I didn't understand, sir.
But in your NCERT textbook, I mean, from what I remember, I think they would have used double M only for amines in your NCERT textbooks.
Not too sure, sir. I didn't study that chapter. I went and.
Oh, okay. Maybe then I'll clarify it maybe 1 second. Yeah, in this book also they have used double M only. Yeah, everywhere it is double M.
Oh, okay, sir.
Yeah, everywhere it is double M only. I don't know what your teacher did, but yeah, use double M and check what is used in NCERT and accordingly use in your exams.
Okay, sir. Okay.
Okay, right. Cool. So another example, if I have to take, say I take K3 Fe C2O4 thrice. Okay, so I have this compound with me, right? So can you name it?
Sir, can you show the? Okay.
Yeah.
Sir, is it potassium trioxalato-ferrate 3?
Okay, you're using trioxalato. Tri cannot be used because this is going to be a bidentate ligand. So I should use tris. Right, other than everything is correct. Right, so it should be potassium. Now this should be tris oxalato, oxalate ion, oxalato ion. And it will be -6. So remember, C2O4, 2 minus is what will be there. So it will be X -6 equal to -3. So X will be +3. So it will be ion 3. Oh, now I have to end it. See, this is a anionic complex. So I have to end with 8. So it should be ion. It should be ferrate 3. This will be the correct IUPAC naming of this compound. Okay, potassium tris oxalato ferrate 3. Right. Okay. Now there are certain complexes where both the cation as well as the anion is a coordination complex. One anionic complex coupled with an anion, one cationic complex coupled with an anionic complex. Right. So at that time, what will you do? Just do the same thing. Maybe we'll take an example. Say, if I had this particular compound, PT, PY 4 times, PY is pyridine, guys. Okay, PY is pyridine as a ligand. Okay, fine. And then PT, Cl4. Okay, now you don't have to worry about how to find whether which one is cation, which was anion. As I already told you, when we write conventionally in chemistry the formulas, I always write the cation first and then I go for the anion. Right? So obviously on the left hand side, what you have is the cation, and on the right hand side, what you have is an anion. That is for sure. Right? Okay. Now, if you want to name it, right? Now remember, pyridine is a monodentate ligand. I don't know whether you have it in syllabus, but still, knowing it is not a big deal. This is also one type of ligand, but it's a monodentate ligand. Okay, right? So fine, I think you'll be able to name it now. Remember all the things whatever you have learned and just apply it here. You'll be able to easily get the answer. Okay. So if you don't named it, it should have been like this. So starting with the cation. So I have pyridine first, right? So it should be tetra pyridine. Now this is platinum. Okay. Now platinum.
Sir, shouldn't it be pyridine or something?
No, it is tetrapyridine. Yeah, it's just pyridine only.
Okay,
Right.
sir. Okay.
Right. So that's tetrapyridine platinum. I will check for the oxidation numbers. Wait, and then if you go here, it would be tetra chlorido platinate. Hope you understand why am I writing platinate, because this is an anionic complex. Okay, right. Now what you have to understand is, guys, this will be a neutral thing. This will be a pyridine is a neutral ligand. So whatever is the oxidation state for this, that will be the oxidation state here also. Okay, and obviously platinum is one thing which is not capable of giving me so many oxidation states. Only one is possible, that is +2. But even if you don't know that, how do you calculate here? Okay, so if this is X plus, this should be X minus. Okay, and I have two equations and two unknowns. But again, you don't have to worry about this. If they give you platinum, right? Remember that it is actually going to be only +2 possibility. But let us try whether we are getting +2. If I do any
Sir,
kind of, yeah,
both the platinums will have the same oxidation state, right?
yeah, yeah, it will be like that. Yes, both the platinums will be +2 oxidation state only. Okay, right. So let us calculate what we have here. Try to do it. Um, so if I do for this, X, they should not be giving it like this actually. Write X.
Sir, can we solve it like this? Like 2 into x minus 4 equal to 0.
Okay, that is possible, right? Yeah, good way to think about it. So you see that there are two. No, totally, we'll just calculate instead of going for this cation and anion separately. The overall charge of this is 0, right? So I can do it like 2 into x for platinum. Pyridine is having 0, right? And chlorine is having -1. So -4 is equal to 0. So yeah, x will be first. Good way to go about it. Okay. So now not only in this complex, people, any complex which is a both cation and anion to be a complex molecule, right? You will generally find both the elements, both the metal ions will be having the same oxidation state. Okay, right? So that I think will be, now you'll be able to name any type of complex given to you. Okay, right? So we'll move on. We'll move on to maybe a little bit of valence bond theory. Then we'll go for crystal field theory, and then we'll go for isomerism. Okay, right. Right. So valence bond theory is basically your hybridization theory. We already know how hybridization works. We have spent quite an amount of time in chemical bonding. Okay, right. But if you can remember, in chemical bonding, I told you with the help of hybridization calculations, right, you will be able to find how many coordinate bonds are going to be there in a particular molecule. For example, if I have taken BF4 minus, okay, if you have taken, for example, if I have taken BF4 minus, right? Okay, now I know boron is going to have 1s2, 2s2, 2p1. Am I right? Yeah, 5 as the atomic number, right? Now, if I look at the valence shell, now first of all, let me calculate the hybridization here, right? Now we know how to calculate the hybridization with the help of steric numbers, right? Now that steric number is equal to a number of atoms bonded to the central atom, number of atoms bonded to the central atom plus the number of lone pairs in the central atom, right? Number of atoms bonded to the central atom plus number of lone pairs in the central atom, right? Now central atom is boron, and to which 4 fluorine atoms are attached, right? So one of the components of this is 4, and the other component talks about number of lone pairs, and that obviously, you know, boron is not going to have any lone pair, right? So it is 4 plus 0, steric number is 4, so I know I'm going to have sp3 hybridization. This we know how to calculate, right? Now what we do is, let me make the hybridization. So I have 2s having 2 electron and 2p having 1 electron. So let me shift it here, right? If I shift it here, I will be getting this, right? Now see, understand that I have to go for sp3 hybridization. So I have s1, p1, p2, p3. This entire thing will form 4 numbers of sp3 hybridized. All these are sp3 hybridized orbitals, and 3 of them are going to have 1, 1, 1 electron, right? And obviously 3 fluorine atoms are going to give 1, 1 electron here, right? Now you see the other one is empty, right? So what do you mean by this? is that this empty orbital shows me, the empty hybridized orbital is showing me that the other fluorine atom, F minus, which is there, is going to donate 2 electrons, making a coordinate bond. So if I have to make the structure properly, this is how I write. This fluorine F minus is going to donate 2 electrons to the empty orbital of boron, making it an empty hybridized orbital. Okay, just give me a moment. I'll be back in a minute. Just give me a minute. Okay, sorry guys, there was a thing I had to take care. Okay, so we are talking about hybridization. So hope you understand. So when how can you decide the number of coordinate bonds in a particular molecule is by looking at the number of empty hybridized orbitals. Okay, as many as empty hybridized orbitals you have, as many number of coordinate bonds you're going to have in the molecule. So in this case, you had only one empty orbital, hybridized orbital, so there is going to be only one coordinate bond. right? Now, if I apply the same thing in case of your coordination complexes, right? Now you know that the entire molecule is basically only coordinate bonds. So if you look at the central atom, whatever is there, if you check the hybridized orbitals, all of them will be empty, making sure that all of them are going to be coordinately bonded to the ligands. Okay, right? So now if I can take some examples, is going to help me. Right, say I take nickel Cl4 2 minus. Okay, right. Now they will, this kind of question will definitely come. They'll ask you to draw the hybridization diagram, how is it forming and all that. Right, they'll ask you. With the help of this, you'll be able to even find the magnetic moments. Magnetic moments, you know, will be the will be equal to root of n in 10 plus 2, where n is the number of unpaired electrons. Right. Okay. So first, what you have to do is find the this thing. What is that? Oxidation number. Right. So if you can see, oxidation number will be +2 if you calculate. Right. Now, next thing what you have to understand is you have to look at the coordination number. Now, coordination number here is 4. Right. So when you have coordination number 4, you can have two types of structures in coordination compounds. In general inorganic compounds, I will have only tetrahedral shape. Right here, there are two things possible. One thing is tetrahedral. The other one is going to be square planar complexes. Two types of shapes are possible. Okay. Now this you can decide with the help of what is the hybridization. If you find that this metal atom is sp3 hybridized, then it is going to be tetrahedral complex. And if you find that it is actually going to have dsp2 hybridization, this is inner d orbital. Right, this is inner d orbital. If you are going to have dsp2 hybridization, then I can decide it is going to be a square planar complex. Okay, now I have different names for also these complexes. So since this is using an inner d orbital, right, this kind of square planar complexes are also called as inner orbital complexes. Right, this is also called as inner orbital complexes. And obviously these are going to be called as outer orbital complexes, because it is only having valence shells, valence shell and valence s and valence p. Right, so tetrahedral complexes are going to be called as outer orbital complexes. Okay, so anyways, so moving on, if I take this example, first thing what I have to look at is the oxidation number and the coordination number. If you look at, so either of these two are going to be the possibilities. Right. Okay, now I know nickel. If I take just nickel, I'm going to have 4s2 3d8 as the configuration. Right, now if it is going to be Ni2 plus, please understand that you will always remove electron from the valence shell. Right, so the valence shell here is 4s, so for this it will be 4s0 3d8. Okay, right. And next thing what you have to understand is, guys, there are something called as weak field ligands and strong field ligands. Okay, now weak field ligands, strong field ligands, how do I do it? We don't have any theoretical concept behind it. All these are experimentally proved things, in the sense that I go for something called a spectroscopy, right? So with the help of that, I'll be able to check which is forming a stronger bond, which is forming a weaker bond with a metal, right? So whichever forms a stronger bond will be a strong field ligand, whichever forms a weaker bond will be a weak field ligand. Okay, right. So hope you know there is something called a spectrochemical series, right? So basically, spectrochemical series talks about the strength of the ligands, the order of the strength of the ligands, right? So if I have to give you the exact order, spectrochemical series. Second. Okay, fine. Maybe I don't need them. I can just start, say, generally X minus ligands would be weak field, right? Even your OH minus ligands would be little weak field, right? NCS will be a weak field, right? So I can actually go in this order. But again, it is actually going to vary. Like I can just tell that these are weak field ligands, right? Now I have, say, something called as intermediate ligands, which are generally strong only. Say it is going to be water, ammonia, NCS, yeah, sorry, SCN. Okay, so those kind of ligands will be intermediate ligands. And the last thing is a strong field. If you look at, right, say I can have EN, EDTA, CO, CN, all these things will come under strong field ligands. Okay, so what you have to understand is whenever you have intermediate ligands or strong field ligands, right, what you have to go for is pairing. Okay, that electrons in the valence shell are going to get paired because of these strong field and intermediate ligands. Now, why that happens, we will be able to get the answer when I go for crystal field theory. Okay, so for now what you have to understand is if you have intermediate strength of ligands and the strong field ligands, you have to pair up the electrons with the valence shell of the metal, right? And if you have any weak field ligands like this, you will not go for pairing. Whatever is there, you will keep it as such. Okay, right. So now keep all these things in mind: strong field and intermediate pairing, weak field no pairing. Okay, right. So now if you keep these things in mind, just the spectrochemical series is given in your textbooks. Just go through it. Okay, they will give you an order. This is more stronger than this, that is more stronger than that, something they'll give you. Not important, but if you can know it, well and good. Okay, so you have basically for Ni2 plus 4 is 0 and 3d8. Okay, right, fine. So now 3d8, obviously I will have what, 4s. If I have, basically I'll have 4p and 4d also. Or let me write it like this: 3d8, 4s 0, 4p 0, 4d 0. No issues. Okay, now in 3d I have 8 electrons. 3d I have 8 electrons. 4s is having 0, 4p is also having 0, 4d is also having 0. Okay, now what we have to make sure is you have to make sure that there are 4 orbitals coming, and they will either should be able to form sp2 or sp3 or dsp2. That's the only possibility, right? Now if you want dsp2 coming, this orbitals should be the d orbital, inner d orbital. This is 3d. This should involve in bonding, right? But you see, there is no possibility. There are already filled electrons here. There is no possibility, especially with the help of a ligand like chlorine, no pairing will happen. There is no possibility that this can involve in the bonding, coordinate bonding, because I should have empty orbitals, right? So the only possibility I can have is to go for sp3 hybridization. This is 4s, this is 4p, combining together to form sp3 hybridized orbital. So now keeping this in mind, you can easily tell that NaCl4 2 minus complex will be a tetrahedral complex, and it will be an outer orbital complex because it is having sp3 hybridization. Right, now if I change the ligand, right, so if I change the ligand to, say, if I had NaCl4, if I had changed it to NiCN4 twice, 2 minus. Okay, now in this case what is going to happen, right? Now I told you Cn minus will be a strong field ligand, right? So now if I write 3d8, 1 2 3 4 5 6 7 8, and 4s and 4p are also 0. 4d you leave, you don't have to mention that. Okay, so this is 3d8. Now this is going to be the case when the ligand is not present. But when the ligand is present, I told you that the pairing can happen. So these two electrons can pair up to form something like this: 1 2 3 4 5 6 7 8. Okay, this pairing can happen. Right, now you see I have one d orbital empty and one 4s and 4p's are there. Now this orbital became empty because of pairing, so this inner d orbital can involve in bonding, right? So you'll have d s1 p1 p2 forming dsp2 hybridization. Okay, right? So when you have dsp2 hybridization, we know that the complex is going to be an square planar complex, and it is going to be called as an inner orbital complex because an inner d orbital is used. Okay, now one thing you can know for sure from this whatever we did, for you to have inner orbital complex, for you to have square planar geometry, you need to have strong field ligands, or else it is generally not possible. Generally not possible. That's the thing you can keep in mind. Okay, so for the same ligand, for the same metal atom, if you have one case strong field ligand, the other case weak field ligand, right? Generally, the strong field ligand would be a square planar complex, right? But again, do not go with any assumption. Just do the things whatever I told you and check whether you have any empty inner d orbital empty. If it is there, yes, it can undergo dsp2 hybridization to form a square planar complex. Okay, so that is about your valence bond theory. Okay, like so many examples will be given in your books, you can try it out, right? Maybe I'll give you one example for a octahedral complex. Right, say octahedral complex, let me take CO F6 3 minus. Okay, CO F6 3 minus. Now this is a octahedral complex. Now here also you can have inner orbital complex and outer orbital complex depending on whether the inner d orbitals are involving in bonding. But here there is no difference in the geometry, right? So the two geometries possible are going to be D2sp3 and sp3d2. Both of them will have octahedral shape only, right? But again, the properties will be different, reactivities will be different, all that. One thing is going to be called, say this D2sp3 is going to be called inner orbital complex, sp3d2 is going to be called as outer orbital complex. Okay, so again, it is going to be depending on the ligand. Okay, so cobalt is going to have manganese, iron, cobalt, nickel, so 3d7, right? So cobalt will have 3d7 4s2. Okay, now we'll check what is the oxidation state of cobalt. Can I say it will be +3 here? If you calculate x minus 6 equal to -3, x will become +3. So it is cobalt is in +3 oxidation state. +3 means obviously I have to remove the 2 electrons from the valence shell and 1 electron from the penultimate shell, that is 3d7, which will become 3d6 4s2. Okay, 3d6 4s2. Okay, right. Now if I write the orbitals along with electrons, 4p also 0, 4d is also 0. Okay, 1 2 3 4 5 6, Hans rule. Remember, you have to follow it. And this is 4s, this is 3d, this is your 4p, this is your 4d. Okay, now here I have F minus, which is a weak field ligand, so pairing is not possible. So you have to take only the outer orbitals. Valence shells only are possible. So the only possibility is S P1 P2 P3 D1 D2. So this is gonna form sp3 D2, and it's going to be an outer orbital complex. Okay, right. So if I have to give you an example for an inner orbital complex, just take this down. I'll give you that. Okay. So let me take Fe Cn 6 times 4 minus, right? Yeah, correct. Right. So Fe Cn 6 times 4 minus I have taken. Same thing, same exact procedure. So first Fe, if you calculate, will be in +2 oxidation state. Okay. So it will be iron, cobalt, nickel. So it is going to be 3d6 for iron, will be 3d6 4s2, and if it is +2, it will become just 3d6 4s0 4p0 4d0. Okay, now let me draw the orbitals. 1 2 3 4 5 1 2 3 4 5 6, right? 4s0 4p0. Okay, right. Now this will be the case if the ligand is not there, or if the ligand is going to be weak field ligand, right? But what I have here is cyanide again, which is going to be a strong field complex, or I mean not strong field complex, a strong field ligand. So pairing will happen. So if pairing happens, can I say that it is going to be something like this: 1 2 3 4 5 6, right? And then you see this, and I don't have the d. I don't want the d. I don't want the d orbital for d. I don't need to have. So you see there's d1, d2, d3. I mean d1, d2, s, p1, p2. So it's going to be d2, sp3. I should take sp3. I'm sorry. It should be d2, sp3. You see there are two empty d orbitals. The inner d orbital is empty, so I'm able to take it. Okay. So like this, questions can be asked. Prove that with the help of VBT, prove that that complex is going to be an outer orbital complex or an inner orbital complex, or they say that prove that it is going to have tetrahedral geometry or square planar geometry. This is how you'll be able to do it. Okay, right. So that's about valence bond theory. Now, what it does not tell me, right? What it does not tell me is the weak field and strong field ligands. We took the idea from actually some other theory, right? So it is not explained why this is a strong field, why this is a weak field ligand. And second thing which is not told is about the magnetic properties, right? Magnetic properties in the sense whether it's paramagnetic or diamagnetic, or say now we can look at it and tell maybe with the help of or say actually that is also told. If you have unpaired electron, I'll be able to tell that it's paramagnetic. But what it is not telling you is about the stability of the complexes. Okay, so certain things should be stayed at -20°C. Certain things should be stored under say higher temperatures and some other pH, some other buffer, something, right? So those stability questions are not answered by VBT. Okay, right. So because of these reasons, now we'll go for crystal field theory. So CFT. Okay, right. So CFT has its own assumptions. Okay, so CFT, what is it going to assume is that my negative ligands, negatively charged ligands, right? I'm going to call it as point charges, right? And when I have a neutral ligand, that is treated as a dipole, point dipole, right? And what you have to understand is here, the CFT is going to take the interaction between the metal ligand interaction is purely electrostatic, right? Purely electrostatic, basically in the form of attractions and repulsions only we are going to speak, right? Not in the form of anything else, not in the form of say that you saw that electrons are going to go to these orbitals. No, not so much in depth. Majority will be speaking only in terms of electrostatics. Okay, in the metal ligand interaction is going to be purely electrostatic in nature. That's what this considers, CFT considers. Okay, right. Then what it says is that, right, so when the metal alone is there, right, when the metal alone is there, it will have degenerate d orbitals, right? Degenerate d orbitals. We know what is degenerate. Degenerate means same energy, right? So I know the metals will have 5 d orbitals: dxy, dyz, dxz, x squared minus y squared, and z squared, right? So all these orbitals will be of, all these 5 orbitals will be of same energy, right? But when the ligand is approaching, the metal, right, when it is a little far away, when this is isolated, metal now is now isolated, then it is degenerate. Okay, now when the ligand is approaching the metal, right, so what is going to happen is the repulsions are going to come into the picture, right? Repulsions of electrons possessed by this and some electrons present in the metal, they're going to undergo repulsion. Okay, now as long as the ligand is little far away, right, all the 5 d orbitals will experience the same amount of repulsion. Okay, all the 5 d orbitals will have same amount of repulsion, right? But what will happen is, since all of them are experiencing repulsion, their energy is increased, right? Say for example, initially all the 5 d orbitals are in this energy, like this is the energy curve, right? Now when the ligand has approached the d orbitals, all the 5 d orbitals went to higher energy, and the ligand is approaching. This is without ligand. Here ligand is there, here ligand is not there. Okay, right? All the 5 d orbitals energy are increased because of repulsion due to the metal ligand bond which is getting formed. Not exactly, the ligand is a little far away. Okay, right. Now when the ligand is very close to the, right, when the ligand is very close to the metal, right, now the degeneracy of the d orbitals is lost, right? That means what? Now the 5 d orbitals are not going to have same energy. Some of them are going to have higher energy and some of them are going to have less energy. Okay, now what we need to understand why this happens, right? So if you want to know why this particular thing happens, right, you have to understand how the ligand approaches, right, and what directions the ligand approaches, and what is the orientation of all these 5 d orbitals. You know what is the shape of these orbitals, right? So the shape of the d orbitals matters, and the directions in which your ligand approaches, those things also matters. Okay, right? Fine. So keeping all this in mind, right, so we will go for how this splitting is happening, how the degeneracy is lost, and because of it, what other things is going to happen, right? All these things we'll see. So these are all the assumptions, or say these are all the postulates of crystal field theory. First one, negative charges, point charges, the neutral ligands are going to be point dipoles, right? And the metal ligand interaction is going to be purely electrostatic, either repulsions or attractions. And then when the metal alone is there, right, it is going to have degenerate orbitals. Now when the ligand is approaching little closer, all the energy of these 5 d orbitals are increased equally. Still they are degenerate, but when the ligand has completely approached, right, now the degeneracy is lost, right? That means some of them are going to have higher energy, some of them are going to have lesser energy. These things alone you remember. Okay, right, moving on, right? Say let me take an octahedral complex first. Okay, I'm going to take an octahedral complex, right? Now obviously I know octahedral complexes will have 6 ligands, right? L6, 6 ligands are going to be there. They're the same type or different type, doesn't matter for now, right? There are 6 ligands. Okay, now what you have to understand is, guys, you know how the octahedral shape looks, right? This is how the octahedral shape looks, right? 6 ligands are going to be there. Now, or you can visualize it like a square bipyramidal shape. I have a square, this is a square, one pyramid and bottom pyramid. It is also called as square bipyramidal complex, but generally we call it as octahedral. Anyways, what you have to understand is all the bonds are actually 90-degree apart, right? All the bonds are actually 90-degree apart. This bond angle is 90, this bond angle is 90, everything is 90, 90, 90, everything is 90 degrees. Okay, now if everything is 90 degrees, can I say the directions of ligand approach, since they are mutually perpendicular, right? Can I say there are going to be 6 directions of ligands wherein which the 6 ligands are going to approach, The 6 directions can be x, y minus y, y minus y, z, and minus z. These 4 will be the directions of ligand approach. Is it not? Right? Because obviously all these are going to be mutually perpendicular. X and minus x will be 180 degree apart. Say, for example, this is x, this is minus x, right? This is y, this is minus y, this is z, and this is minus z. 6 directions. Okay, right? So these are the directions of ligand approach in an octahedral complex. Okay, right, fine. Now this we understood. Now what I have to understand is, what are the shapes of the d orbitals? Okay, now please understand, people. I have dxy, dyz, and dxz, right? All these orbitals are pointing in between the axis. For example, if I take dxy, right, say obviously this is y-axis, this is x-axis, right? So you know the shape is going to be a double shape, something like this, right? So you see the lobes or the electron density of these are not along the axis, it is in between the axis, in between x and y axis. If it is dyz, it will be between y and z axis. If it is for xz, it will be between x and z axis. What you have to understand is the lobes are pointing in between the axis. Okay, fine. Now, but if I take the other two, that is, if I take dx squared minus y squared and dz squared, right? What does it say? If I write dx squared minus y squared, you'll see this is my y direction, this is my x direction. Now what do you see? 4 lobes, right? 4 lobes are pointing along the xy axis, along the xy axis. And obviously if I take dz squared, I know how is it going to look. This is my z axis, 1 lobe here with a ring surrounding the lobes. Again, what you see is that it is pointing along the axis, along the z axis. Okay, fine. So now you know the directions of ligand approach. These are this, and you know what are the shapes of the 5d orbitals now, which is pointing in between axis, which is pointing along the axis. Okay, now obviously now when the ligand is going to approach, right? When the ligand is going to approach, I told you that all the 5d orbitals are going to experience some repulsion and their energy is increased, right? Okay, now when the ligand is very close, can I say, since these are the along the axis, along x, y, z axis only the ligand is approaching, right? The d orbitals which have their lobes pointed along the axis will suffer more repulsion. Isn't that? Say this is my xy plane. Obviously, the ligand is going to approach in this direction. Say ligand is going to approach in this direction. Ligand is going to approach in this direction. Right? So since the ligand approach directions and the lobes, how their points are same, that is along the axis, that kind of orbitals will suffer more repulsion than the orbitals which are having their lobes pointing in between the axes. This point is clear. Everybody understood what I'm trying to say?
Yes, sir.
Right. Now this we understood. Then you know how the degeneracy is caused. Is it not? Because it is not the equal amount of repulsion which the d orbitals are facing. Two of the orbitals, namely dx squared minus y squared and dz squared, which have their lobes pointing along the axis, will suffer more repulsion. So their energy is little higher. Right. And these orbitals, these 3 orbitals having their lobes pointed in between the axis, will suffer lesser repulsion. So they will have lesser energy. That's it. Now this you understood. Then we can easily go for this. Right. So if I put it in the form of a diagram, right, the energy profile diagram, this is energy. Right. So now only the metal is there. Right. So metal, only metal, say 5d orbitals, all of them are equally distinct, very less energy it has. Right. Now when say the ligand has approached, right, when the ligand has approached, now say the energy of these orbitals are increased when a little close by. Right. Now when the ligand is very close to each other, now this also will split. Right. Now this also will split to one higher energy state and one lower energy state. Correct? Now, in the higher energy state, you are going to have two orbitals. In the lower energy state, you are going to have three orbitals. And obviously, we know this is x squared minus y squared, and this is dz squared, and this is xy, yz, and zx. Okay, now this splitting will happen, right? Now I don't want to talk call it as your anymore dx y y z z x y minus y z and all that. We'll give you some other terminology for this. Okay, now these three orbitals together are now going to be called as T2G orbitals. Okay, now there is a reason why I'm going to call it as T2G, but again, not important to you. Okay, it comes from some symmetrical approaches and stuff, but anyways, so these three orbitals put together is going to be called as T2G set of orbitals, and the higher level, these two are going to be called as EG set of orbitals. Okay, T2G, EG. T2G will have three orbitals, EG will have two orbitals. In this case, what you see is that the EG orbitals are of higher energy and the T2G orbitals are of lower energy. Okay, just give me a moment, guys. 1 second, I'll be back. Okay, right. Fine, so this we understood. Right, okay. Now if I have to place the electrons on all here, what is the time? Okay, I can finish this. Okay, so if I have to place the electrons on all here, right, so now that at that time again, the what type of ligand you have, all these things matters. Okay, now the splitting is very, very important. Okay, and one more thing also you need to understand, right? So this, the center, this is not a center point. Please understand, this is not equal. Say this is 50% and this is 50%. No, right? So what I'm trying to tell you is that this is decreased to 50% energy and this is decreased to increase 50% energy. No, that is not like that. Why? Because I have two different numbers of orbitals. Here I have three orbitals. Here I have only two orbitals present. Okay, so this energy gap and this energy gap are actually not going to be same. They will actually be different. Okay, now this center point, whatever is in between, the energy of the higher energy degenerate orbital, this is higher energy degenerate orbital, that I'll represent it as delta naught. That I'll represent it as delta naught. Okay, here the increase in energy would be, I think, 4/3 and 2/3. Let me 1 second. Yeah, so this will be 0.4 delta naught, and this energy will be 0.6 delta naught. Mine, I have to put a negative sign. Okay, so this is the delta. Delta naught is the energy of the degenerate orbital, higher energy degenerate orbital. Right now, the non-degenerate orbital, the orbital is not degenerate. Now the higher energy is increased by 0.4 delta naught because I have only two. Right now, this will be decreased by 0.6 delta. And why you have a negative sign is because I'm making sure that there is a stabilization. There is a decrease in energy, and decrease in energy will come by loss of energy. Right, so that is why I put a negative sign. In thermodynamics, we follow energy lost is negative, energy gained is positive. Okay, so this is increased by 0.4, this is increased by 0.6 delta naught. Very, very important. Just don't tell me 0.6 or just tell me 0.4. It is 0.6 or 0.4 delta naught. Okay, right, now this is okay for me. right? Now what I have to understand is, how will I fill the electrons here? Okay, now filling electrons, basically you're going to fill the electrons in T2G set and AG set. Okay, so till D3 you have no problem. D1, D2, D3, no problem, right? Because if I have D3, for example, D3, I'll easily write it as T2G3 EG0. So this is going to have one electron and EG has nothing. Okay, now when I go for D4, that is where the problem comes, right? Now that D4 can have two types of configuration. One can be T2G3 EG1, you put the next electron here, or T2G4 EG0. Instead of this, you pair it here. Okay, two possibilities can come, right? Now how are we going to decide it, right? How are we going to decide it, right, is based on this delta naught, right? This delta naught, actually I will tell you the name. This delta naught is what is my crystal field stabilizing energy. Okay, delta naught is what is it? CFSE. CFSE is crystal field stabilizing energy. Okay, or basically this energy gap is what I'm talking about. Okay, so this energy gap is what is my crystal field splitting energy, sometimes we call it, sometimes we call it crystal field stabilizing energy, but anyways it is going to be CFSE, right? So we are going to compare this CFSE with one more energy term, and that energy term is basically going to be my pairing energy, right? Now pairing energy means, obviously now if after all you want to pair the electron like this, right, you have to overcome the repulsions, right? So obviously when you want to overcome the repulsion, you have to spend some amount of energy there, and that energy is what is called as my pairing energy, pushing the electron against the force of attraction, sorry, force of repulsion, right? That energy is what is called as my pairing energy. Okay, right. Now depending on which is going to be higher or lesser, now I'll be able to tell which is going to be what. Okay, now please understand, say there are going to be only two cases, right? Case one is CFSE, that is the energy gap delta naught, is very greater than the pairing energy. That means what? Between the T2G and EG set, there is a huge difference. There is a huge difference, energy gap, right? So obviously, if I have to put the electron here, now always remember, as I already told you, in chemistry, right, whatever happens will happen with the expense of minimum amount of energy. Whichever place, whichever process, or whichever pathway where I'm going to spend least amount of energy, that pathway only is taken by default. Okay, now for me to put the electron in the EG set, I am requiring higher energy than to put the electron in the lower energy orbital and pair it, right? So whenever you see this particular case happening, you will always see that the electron is going to get paired, right? So if I have D4 configuration, and if I check that if the CFSE is greater than the pairing energy, then it will eventually try to pair, because there only I have lesser energy. Okay, now second case is when I have delta naught lesser than T, that is for pairing energy supply more energy than the energy gap, then definitely again the electron will prefer to go to the higher energy state, and in that case you will see that first T2G3 EG1 will be the configuration. Okay, so like this you will be able to decide. Okay, now sir, okay, pairing energy might be, I'm like, don't have to worry about pairing energy, it is just going to be an electrostatic force of repulsion. How do I decide this? How do I decide the delta knots? Okay, now that is going to depend upon the ligand, right? So if I look at it, factors affecting CFSE, that is factors affecting delta naught, I'll tell, right? Factors affecting delta naught. One thing is the strength of the ligand, right? Now remember, more and more strength of the ligand, more and more will be the delta naught, because more and more will be the repulsion, is it not? So this strong field complexes, the strength of the ligand, the strong field complexes are going to have very high amount of electron density, right? So they will have higher amount of repulsion inducted into the metal. Okay, so in that case, the splitting will be very, 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 very high. The splitting would be very, very high, right? So that's the reason why I told you that the strength of the ligand is directly proportional to the CFSC delta naught. Okay, right. Now you can understand why when we spoke about BVT, I told you that when you have a weak field ligand, then it can go okay, right? But if I have a strong field ligand, then pairing has to happen. That's exactly what is happening here. If I have higher strength of the ligand, this particular case will become true. Delta naught will be there with the pairing energy because I have a very strong field ligand, right? So now what will the electron prefer to do? The electron will prefer to undergo pairing. That is the reason why when I say when I have strong field ligand, you have to undergo pairing is because of this. Okay, right. Now there are other cases also. The other case I would say would be the oxidation state of the metal. Right? Say if in one complex I have +2, in another complex I have +3. Obviously, more and more positive charge, more and more will be the repulsion, isn't it? So more and more will be the CFS. Right? So oxidation state, if I have Mn2 plus and Mn3 plus, Mn3 plus complexes will have more delta naught than compared to your Mn2 plus complexes. Okay. Now there is just one more point and we'll wind up. The last point is about when I have 5D elements, which will have more splitting than the corresponding 4D than the corresponding 3D elements. Right? So when I have nickel compared with palladium and platinum, platinum is going to have very high amount of delta. Okay. Now the reasons is because again of the bigger size, more number of electrons, more amount of repulsion. It's all boils down to this attraction and repulsion. Okay, right? So that. So what is the time? I think. Yeah, I think we have 5 more minutes. Okay, so we'll wind up. Right. So now we saw how octahedral complexes are going to have, right? How the splitting is happening. The factors affecting delta naught or delta T. We will see a tetrahedral complexes also. At that time, we'll call it as delta T. Right. Factors will be exactly same. Factors affecting, but little variation would be there depending on how the splitting is going to happen and all that. We will have a difference, right? So we will look at tetrahedral complexes. We'll also look at square planar complexes, how that splitting happens there. That I think you'll not have it in your NCERT textbooks. So that we'll see how it happens in square planar complexes. And with the help of crystal field theory, we'll try to say, okay, this complex is more stable, this complex is less stable, and all that with the help of CFSC value, which will calculate. I told you how to calculate the value. We will be able to do that also. Okay, and with that CFT will be over, and we'll go for isomerism. So tomorrow, in another 45 minutes, I'll be completing this, and we'll go for a couple of problems. Okay, fine. Any doubts? Any questions from this? Okay, fine, cool. Thank you, guys. We'll meet again tomorrow. Thank you so much.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.